This is video 14, exploring COBS frames in serial transfers on STM32 MicroPython and a desktop Python application. The code for this video is at the GitHub site. The information presented in these videos on MicroPython should work as well on any STM32 F4 board. All code examples have pin definitions at the beginning of the file to allow the programmer to alter as needed. As this channel covers multiple microcontroller solutions over time, please subscribe to stay informed and click like, as that really helps. In this video, we continue to explore frames by using the COBS algorithm to build and decode our frames in serial transfers. Through internet searches, we locate 3 COBS code examples. We will verify their encoding and then use their example. COBS is consistent overhead byte stuffing and is described by Wikipedia as an algorithm for encoding data bytes that results in efficient packet framing. It uses 0 for frame delimiters, and the algorithm ensures there is no other 0 throughout the frame. This results in a very small and consistent overhead in its byte stuffing, hence the name. COBS is only the algorithm for the encoder and decoder. In this example, the encoded byte array is only 1 byte longer than the source. Using the HDLC algorithm, an escape byte would have inserted before the bytes FE and FD, making the encoded string 2 bytes longer. The algorithm is based on research in the paper by Stuart Chester and Mary Baker. A link in the endnote will provide a copy of their paper. The Wikipedia site has 11 encoding data examples. This can be used to verify any code libraries we locate. Through our continued internet search, we locate 3 different implementations of COBS in Python. First, Craig McQueen deposited his code in the PyPI Python package software repository. His code, though, only has the Python code for the encoder and decoder. In the EEV blog, the submitter Volts and Jolts provided zip code files with the COBS code and an example desktop program to send GET messages. In the MicroPython forum, the submitter Planet9 provided both desktop and STM32 code to send GET messages. Interestingly, Planet9's STM32 code used the async library. I collected these 3 code examples, and given that the code is 4 years old, I needed to update a few statements. The code is at my GitHub site and is organized as shown in this README. Here you can see that I've created versions for all 3 platforms for the driver files. There's driver files for the STM32 and there's driver files for the desktop. The driver files for the STM32 are loaded onto the flash directory of the STM32 and can reside in the main directory or in, normally, a lib directory. The desktop drivers are placed just next to the file that we're going to use to test it. I then created test programs for every single platform. And this was to ensure that the encoder-decoder function still worked after I migrated the code across the different platforms and to the different versions of MicroPython or Python. Finally, the last 2 programs included send-get functions. So I modified those programs so that they would work both as loopback mode or as the ability to connect across the Bluetooth connection that we did in the last video. And so we'll actually show that again this time. Finally, Planet9 included code for the async functions. So we'll run his code, his async code, and have it connect to one of these desktop applications. For the desktop programs, we will use Microsoft's code editor and invoke Python in the terminal. The STM32 programs will be run from Thony. Let's look at the code. In this first example, we're going to run code from Craig McQueen's COBS encoder and decoder. The others will give the same results. So what I did is I created a program so that I would have messages that were very similar to the messages as described in the wiki site. So in the wiki site, they used an uncoded data of hex 0, and it should result in 0101 and so forth. So we've set up messages for all these different examples, and I just stopped after 4 or 5 examples, and we're going to produce encoded values to see if we get the same as the wiki site. Bear in mind that I did not include the blue 0 byte because, as the wiki site says, this is actually part of the end of packet delimiter, and it will be provided in the send and get functions. In my test, I print out the message, I encode the message, and I decode it. So I'm going to show all 3 versions. All right, so let's try it on the desktop. All right, let's move the screen up a little bit so we can see it and compare it to the wiki site. So in the wiki site, we needed to encode 0 as a 0101 because we don't want any zeros in our message. So this is an offset to the first byte, which is an offset to the 0 end byte. And it got the same value as the wiki site, and it decodes back. And the same for the next example. 00 becomes 010101 and decodes back. The next message is 001100. It encodes to 01021101 and decodes back. So I felt pretty good about that. I ran and tested this encoder decoder for each of the 3 different examples using the encode decode functions that the submitter provided. All right, now that we have verified that the encoder decoder functions are working, let's check out the code. So we're going to switch to volts and jolts example. And we're going to run on the desktop the send and get function. Before I run it, let's make sure that we're in loopback. Okay, we'll save that. And the program is very simple. I've set up the keyboard S key to send the message hello, encode it, send it, and then since we're in loopback, the get message will receive it and decode it. So let's run it. We'll type Python and then test. Okay, it's waiting for us to press the S key. We need to hold it because I've got a little delay there. And I've run it a couple times here. You could see it sent the message hello, which was then received and printed out the message hello. So it encoded it, put it into a frame, sent it, and then received it. All right, let's do the same on STM32. We'll put it into loopback. And we'll do that by sticking a wire in pins A9 and A10 on the STM32, which is the UART pins. And we'll stop the program. Make sure the loopback wire is in. It is. And we'll run the program. Here we have a user button that when we press it, it takes the message hello, sends it where it's encoded and put into a frame, sent to the UART where it's then read by the get message function and parsed out as the data received. Press and hold the button for a second. Okay, here it sent the value hello. I added some print functions in the driver so that we could actually see the frame. So there's the frame with the 0 delimiters. The 08 is the byte that the COBS algorithm inserted into our payload. And the last 2 bytes are the CRC16 checksum. So for this example, we moved from a single byte checksum to 2 bytes. This was then sent, and since we're in loopback, this function receives it. I put some extra print statements into the driver, which reads each byte. And so here you see it's parsing out each, it's receiving, reading each byte, and then parses it into the message hello. Well, just for fun, I thought I would add 2 more user buttons. The first button is going to trick the encoder by sending 01, 02, 03, 04, and 05 and to see if it will attempt to read it. Let's try it. Okay, so when I press the button, it sent to the UART 1, 2, 3, 4, 5, which, as you can see by the receive in the driver, it did read 1, 2, 3, 4, 5, but it refused to parse it and print out a message. So it basically threw those bytes away. Let's try another trick. So I set up user button 3 to really trick it this time. Here I've got a start byte of 0 and an end byte of 0, which is similar to what a proper frame should look like, as you see up here. But then I've just put in some random bytes in the middle. So it's not a properly formatted message. It should just ignore it as well. Let's give it a try. All right, so we sent out the message. Here it is sent. And as you can see, I'm just using UART to write. I'm not using the send message. Otherwise, it would have formatted it correctly. And it did read into 00, 11, 12, 11, 0, but it's not a proper frame, so it ignored it. And just to prove it, I will press it again, but this time user button 1, where I have the hello message being sent using the send message function, which formats the string correctly. And you can see this time the receive function read in all the bytes and felt that it had a proper message and parsed it out as the hello. Okay, now that we know the loopbacks are working, let's take the loopback wire off. We'll put in the Bluetooth UART module into the STM32. We're going to just stop and restart this so that it will recognize that device. Okay. We'll come back to our desktop application. We'll go modify it, take it out of loopback. Here, let's stop it first. Take it out of loopback and put in the proper serial connection and save it. Okay, and now let's run the Python program again. So if you recall from our last video where when we connect the Bluetooth, this won't connect because it's trying to connect across this COM port 5 unless the Bluetooth is first working on our STM32. So here it is. It's already running on STM32. The STM32 is waiting for somebody to send it data. The desktop is waiting for somebody to send it data. Or, in the case of the desktop, I can press the S key to send data. So let's move it over to the side a little bit. Move this to the left so we can watch them both operate at the same time. All right, now hold down the S key on the keyboard, and I sent hello, and the STM32 received it across the Bluetooth wireless connection and parsed it out. Now we can do the opposite. We can come up to the user button on the STM32, press its button, the user button, which takes the message hello, and as you can see, it was received over here on the desktop app. So I didn't put any extra print statements on the desktop, just the results. So you can see what it sent and you can see what it received, but it's essentially doing the same thing. Well, it is doing the same thing. All right, so let's try the same trick that we did before. Remember, before we had user button 2 send 1 2 3 4 5. Okay. Now I don't have the extra print statements here. But this will receive the data and ignore it. So press user button 2. Okay, 1 2 3 4 5. Nothing happens. Let's try user 3. Okay, it sent the frame. Nothing happens. Let's try the main user button 1. Okay, and you saw that when I pressed user button 1, it did receive it. All right, that's pretty neat. So not only have we shown that the Bluetooth connection works, we've shown that this framing is also receiving and parsing the data correctly and throwing away any bytes that don't meet the frame standard. All right, let's try and use the Planet 9 program example. So let's stop our program here. We'll come over and we're going to use the Planet 9's example. And I wrote 2 examples here, so you could test it one way, in which I took the desktop code and ported it over to the STM32 and ran his code where the desktop talks to the STM32, but I thought it would be more interesting to demonstrate the async function. So here I've taken his async code and let's take a look at it. And it's doing a lot of async functions. Let's just see if it works. Then we'll walk through the code. So we're going to stop it and restart it so that we can get that Bluetooth connection. Okay, so now it's waiting to send a message or receive. So I can come over here to the desktop, and it can be either the Planet 9 desktop program or in this case the Volts program. It doesn't matter. They both are using the same frame algorithm. So we'll just send this. I hope if I press the letter S. There we go. Pressed the wrong letter. All right, so we pressed the letter S on the keyboard. It sent the letter hello, and you can see that I parsed it out and I added a lot more statements so that we could see what's really going on. But it received all the bytes, and it even does a few things that Planet 9 wanted it to do. So he had it blink an LED. And I added a counter, so every time I run this, it's going to count the number of times that the desktop sends to it. Okay, so now that we know it works, let's go take a look at the code. All right, so Planet 9 wrote this code 4 years ago, and there's been changes in MicroPython and in Python both since then. So let me walk you through what I did. So the first thing I noticed is that he used this function called asyn, and he did not include that, and I could not find that. And that's because that code has changed since then. And what I did is I added the standard async event function that's found in MicroPython and modified the code. And you'll see that we'll get the same features, I believe, that Planet 9 did. So he's using the uasync function on the MicroPython. He's imported it as async. I put all of his driver code into this separate file, which is running on the flash, and he called it UART COBS. I then defined a user button using PB10, and I put the function into this variable user. He had these rather large packets, so I kept those. I set up mine to work with the Bluetooth UART speed. And you can, of course, change the speed of the Bluetooth UART. I just kept it basically standard as you would receive it from Amazon, so that any of you that try this will have the simplest functionalities. So that's straightforward. So this is running this driver code. I then defined what in the async world is called a coroutine. So I defined a coroutine for the user button, which we'll come back to. I defined a coroutine for the blink function. There's also a coroutine for the receive function, but the receive function is buried in this driver. And then a coroutine for this process message. Now he added this, Planet 9 added this because what he wanted to have happen was that when he received a message, that event would get processed by this task and blink the LED. So we'll see that in a second. You see I made a lot of changes here to handle the event in the standard way, which is, in my opinion, much simpler. And also, he had it send back the message, which I could do, but well, I hooked it up to the user button instead. All right, so let's look at the main part of the code. Here, we're initializing a message of hello, right? We set our counter to 1. I'm going to put this hello message into this buffer in the UART COBS driver, okay? And I'm just going to be trying to consistent with what he did. And then we'll do the standard async features. So you have the standard loop where you do a get event loop, and it's going to do a bunch of tasks and then loop forever. So let's look at each of the tasks. So we create an event blink event that's used as the callback in this create task function. Here's where I'm setting the LED 1 on the STM32, and he had a different board, but it turns out that my board also has an LED 1, so I was able to use that as is. I added this. He didn't have this, but I added an event for the push button, which is pretty simple. You just create a task. I'm using that pressed up above, and we'll look at that in a second. I passed it that user variable for the user button. I passed it this callback event, and I also passed it the UART COBS variable. Then I set up a task for the receive bytes. So this function in the UART COBS driver is going to receive the bytes And when it does, it's going to set an event. Okay. And so the next task, this process management task, is going to get that receive packet event. When it gets triggered, it's going to run this event blink callback, as you saw above, and pass it also the CC routine. So now that we have these 4 coroutines that are going to essentially operate concurrently, let's go back and look at them. Okay, so the press function just gets this set up and then enters its loop where it's awaiting a sleep delay. Well, whenever it hits this, it immediately passes control back to the async loop, which allows it to do something else while it's waiting. Okay, but if it gets triggered, in this case, if the sleep occurs, then it's going to check to see if the user button has been pressed. And if it's been pressed, this user button will become 0. Okay, and that occurs when you press it to ground, and it'll send the message. And as we saw, well, we haven't seen that yet, but when we see that, you'll see it's very fast. So that's pretty simple and straightforward. The blink function, well, it's going to come in, do its little setup, and then enter its while true loop that runs forever. And what is it doing? Well, it's just awaiting this event. And what event is it waiting for? Well, it's waiting for the receive bytes event to get set. When it does, it drops through here, lights the LED, prints out the counter information, and waits, and then turns off the LED. So basically, the LED blinks. In this last function, in this last coroutine, the process management, you see it's being passed the receive event. Okay, so it's waiting for that receive event. When it gets it, it sets the blink event. Okay, it clears the receive event, allowing it to do another one, and also it prints out this result. Okay, and that's it. So let's give it a press. I'll just close this up a little bit so you can see it running on the desktop as well. All right, so I'm going to come out here, press it briefly, and you can see that when I pressed it on the STM32, it picked it up. I did put some print statements in, as you saw up here, for the send, so you can see it sent a proper frame, and we received it over here. So this async is rather nice. Well, in summary, we researched the COBS algorithm. We migrated the 3 different program examples that we found and created both desktop and STM32 drivers for the encoder and decoder functions. Then we migrated the 2 blogged examples to the desktop and to STM32, making sure that the encode-decode functions are working correctly. In our testing today, we found we ran the programs in loopback first, just to make sure that they worked. Then we connected the Bluetooth and ran the programs in 2-way communication. First, having the desktop send to the STM32, and then having the STM32 send to the desktop. Finally, we tested the STM32. Oh, we also tried to trick the desktop program by sending random bytes of data to the program, and we showed that the receive functions ignored and would not parse the data, even though it received the bytes, received them and threw them away until it got a proper frame. And finally, we tested the STM32 code using the async coroutines. So, in my opinion, the COBS frames are simpler and are more efficient. And in the next video, we will work with a program that manages the payload to provide an effective way to pack and unpack data in the messages that it sends. So thank you very much for listening,